theory, so we're gonna use the graph theory book. Remember that it is available if if you don't have a printed copy, it is available on the library. You can download a certain number of pages. So, get started with the first two sections, and then at the beginning of the semester, I told you which sections exactly you should, we're gonna use. But for now, you just, first two sections will be fine. Okay, so today I just want to do one more thing that we're gonna need from combinatorics before we move on to graphs. We'll come back to the combinatorics book later. Let's see. So this is section E. It's called the inclusion-exclusion principle. It's in page 63. And we actually have used this idea before. So what's the idea? Let's say that you have two sets. And, I can look at the Venn diagram for those sets. Mm-hmm. Suppose that, well, I have like all these different regions, like everything that's in the union. I have like the outer region. I have everything that's in the union, but in that region, I have like two different types of regions: the intersection of A and B, and then elements that are in exactly one set. What's in A but not in the intersection, what's in B but not in the intersection. Mhm. And what we can write, an expression relating these regions, is this one. If you want to know, you know, if you want to know what's in A union B, then you can take like how many elements are in the union. You can take A, how many elements in A, how many elements in B, but that means that when I add A, I'm when I add A, I'm looking at that region. When I do B, I'm looking at this region, and therefore I added twice the intersection. So I have to subtract it. So when A and B are completely disjoint, I can just say that the total number of elements in the union is the sum of the elements in the sets. But if there is an intersection, by just adding the number of elements in each set, I'm actually double counting the ones in the intersection, so I have to subtract. And we can use that same idea when we have three sets. How can I express the union in terms of the number of elements per set or the intersections? Mm-hmm. So I have A, I have B, and I have C. And so if I want to know what's the number of elements, by the way, the bars are just cardinality, right? So number of elements in that set. So here I want to know how many elements are in the union of A, B, and C. So whatever is inside in the interior of those disks. And so what I can do is I can say, okay, let's do A, the number of elements in A, plus the number of elements in B, plus the number of elements in C. But same as before, when I add A, I'm adding all of that. When I add B, I'm adding all of these. Mm-hmm. When I add C, I'm adding all of that, right? And if I zoom in, there are these tiny regions that are here that are counted twice, or this region here that's blue and green, and
Uh,
then the on top. Yeah.
question: the little bars
Mhm.
over there, is that the same thing as the parentheses, or is there a difference there?
No, these are square lines and it's cardinality. So this is just saying the number of elements of whatever I have inside. So this is the number of elements in A union B, number of elements in A, number of elements in B. Mhm.
Okay.
So because I'm adding these elements too many times, twice, mhm, I'm going to subtract them once. The ones that are in the intersection, I'm going to subtract twice. So I'm gonna do minus the intersection of A union B because those elements were counted twice, like at least some of them. The elements in this small region were counted twice. Once by A and once by B. So I'm gonna subtract them once so that that region is fixed. You see, all of this is okay. This part is okay. This part is okay. This part is okay. Now I'm trying to fix those little pieces, not the triple intersection just yet, but those little pieces. And I can fix that by subtracting the intersections. So here I have, oops. So here I'm gonna have minus the intersection minus so minus the three intersections. No? So I have minus A intersection B minus A intersection C minus B intersection C. Mhm. And now I'm going to look at the triple intersection. The points that are in the center, they were added once here, and once there. And then they were subtracted once here, and once here. Every single element in that triple intersection was added by A, and then again by B, and then again by C, and then it was subtracted by A intersection B because those elements are in all three sets, and it was subtracted here, and it was subtracted here. And so far, I haven't counted them. They were added three times, but then they were subtracted three times. So I haven't counted them. So I'm going to add them. So uh, I'm just going to say these numbers that I added here, these are the number of times that an element in the triple intersection is counted. Make sense? So look, if I have an element that's only in A, and we say, if I have an element there, it's counted by A, but it's not counted by B or by C or by A intersection B because it's not in B, or by A intersection C because it's not in C, or by B intersection C because it's not in B or C, or by the triple intersection because it's not in the triple intersection. You see, it's counted exactly once. Perfect. The same for elements in only B or only C. Those are fun. Uh-huh. If I had if I had an element here, let's say, in B intersection C but not in A, so in B in C and not in A, then it's not counted here. It is counted by B and by C, right? So I'm just going to add a few numbers here. So it's counted here and here. is not counted in A intersection B because it's not in A, not in A intersection C because it's not in A. It is counted here, and it's not counted in the triple intersection because it's not in the triple intersection. So that gives me a total of 1 plus 1 minus 1. So it was counted exactly once, that's what I want, right? And the ones in the triple intersection are the little numbers that I wrote here. They're counted by all A, B, and C, but then they're subtracted by all double intersections, and so they're added afterwards. So everything is counted exactly once. So that's what we want. Okay? So that's the idea. And this is this we can see in these Venn diagrams, but after 3 sets, we no longer have Venn diagrams, at least not with disks. We cannot model that all the possibilities, all the possible intersections when you have 4 sets. So, but we can generalize this idea, and that's what is called the principle of inclusion and exclusion. So in general, we're gonna do that same thing, but I'm gonna need a little bit of notation because because this summation gets complicated. Mm-hmm. So in general, I'm gonna take my. Actually, I don't like the notation in the book as much, but you have the book, and so to make the connection to that, let me tell you what they're using. They are using, if I had, actually, before we go to the general part, let me show you the notation for 3 sets, and then we'll go to the general result. So, books notation for 3 sets. Okay. So kind of what we just did with A, B, and C, writing the union and the intersections like that. This is what they do. S0 is just going to be S0 is just the total number of elements in the universe. So that, U is the universe, everything there. We're not really going to use it. Mm-hmm. S1 okay. S1 is going to be the sum of A, the number of elements in A, the number of elements in B, the number of elements in C. So that would be this, right? That would be S1. Then S2 is going to be the double intersections, the sum of the cardinalities of the double intersections. So the notation so far is fine. What I don't like as much, but I do think that it simplifies the writing, is that they actually write it like this: A, B. So in the book, that's the intersection. That's what I don't like as much. Mm-hmm. But that's how they write it. Okay, so that's how they write it in the book. And so this will correspond to negative S2. And I should probably get started from my negative sign here. So all of them come negative, appear with a negative sign, right? And then S3 is a triple intersection. A intersection B intersection C. And again, the book, to shorten what we write, they write ABC just for the intersection. Okay, so ABC is simply, it's supposed to mean the intersection. And so this one over here will be S3.
Professor, I have a question.
Yeah.
Is S not AU BUC?
The union. Yeah, we're going to use it as the union.
Okay.
Yeah, we're going to use it as the union. Yeah, let's do that. Let's just write here. So that kind of assumes that there's nothing but the union, that the universe is the union. So I'm just going to remove my U from here. I hope that this is really what I want. Okay, if not, I'll come back and check and change it. All right. So what we will get here using that notation is that let me say then instead of so, because it looks like it's not. So then what we have is that S naught is equal to S1 minus S2 plus S3. And so now we can do this in general, right? So now you can imagine that in general, you start with n sets, A1, A2, A3, and so on. AN, instead of ABC, we'll do A1, A2, A3. And so we have, same as before, S naught is just going to be the union of all of them. So all of them together. And then S1 is just going to be the sum of the elements per set. And then S2 is the intersections, all possible intersections. And of course, here I will have to list and choose two of them, right? So, so here I have one term. Here I have n terms, right? And here I have and choose two terms, all the pairs. Mm-hmm. And then I just continue like that. S3 is the triple intersections. This time we have more than just one. All of them. And maybe the last one I'll just list as an -2. Oh, so, So all the triples, n minus 2 intersection an minus 3 n minus 1 an. All the triples. And so here I have, I choose 3 terms. And you just keep going like that. And well, and again, in the book, they, for these, they will just use A1, A2, A3. So they don't write the intersection. So when you read the book, you know what that means. And so in general, I can write the SK. It's just, I'll try to start using a little bit more notation. So it's just the sum of, and you take all the k tuples. Mm-hmm. And so I can say here over all the I1 greater than or equal to 1, less than or equal to I2, and so on. IK, these are different. Sorry. These are, the first one is less than or equal, that was fine. But the others are strictly less. And this one is less than or equal to n. So all n tuples, k tuples. So these are choose k terms. And so the very last one is going to be Sn, which is just the intersection of all of them. And this is just one term, but you can think of it as n choose n. You start with a few terms, more. In the middle, you start decreasing, and then you end up with one term. You know what? Yeah, you know what? I'll go back. Let me say this, because in some of the problems, when we use that complement idea that we've been using before, let me change this. I actually did mean, I'll write it in red. I actually did mean to have here you. So let me say this. So here I actually meant to have you. I'll use a U, a calligraphic U. So U is all that rectangle. Sometimes there are elements here in the problems. So you want everything that's not in the union. There might be elements there. So U is the union and everything that's outside in that universe. Okay. And so really what I want to say here is that here in this one, I'm actually going to write it like the union, So that was an A0, A0. Oh, I said I was going to write it with red, but I'm changing, but I didn't. So this is what I changed. Because, so I'm going to write here. You'll see that sometimes there are elements that are not in the union, and sometimes that's what we want to know. So what I'm going to write is that Yeah. So if you want to know how many elements there are in the union, of all of them, then the same idea as before. We take as one. One more thing that I have to change. So yeah, so I don't want this. So S naught is actually everything, including the union. You'll see why. So this is S1 minus S2 plus S3 minus S4 dot dot dot. And this is minus 1 to the n minus 1 Sn. So the last term can be positive or negative. We just alternate. Sometimes it's positive, sometimes it's negative, but we need to alternate. Mhm. But in reality, many times we need to use that complement idea. So the way that the statement of the inclusion exclusion principle reads is like this. It goes like so it goes like this. If you want to know what's outside, you know, so I'm gonna write it like this: A1 complement, A2 complement. I'll write it with the intersections. Again, I don't like the notation as much. I prefer to write the intersections. So here, A1 complement, AI complement is equal to, so this is the complement of AI. That's what this means. So if you want to know what's the intersection of the complements, so that would be like, so this one is U minus the union. So U is everything, and we're subtracting so this is U minus the union. So everything that's outside in my Venn diagram. So when we were doing 3 sets, if you wanted to know what's outside, so maybe I'll do that here first for 3 sets. This is directly related to our observation. So I'm just gonna say here, in other words, and this is the typical statement for the inclusion exclusion principle. What we say is that what's outside, so A intersection A complement, intersection B complement, intersection C complement, which happens to be U minus the union. So everything that's outside is equal to S naught, which is everything, minus the union. Or so S naught minus the union, and the union is this, right? So S naught minus S1 plus S2 minus S3. You see? So this is cardinality of U minus cardinality of the union, which happens to be, according to our notation, is not minus what we had written before. So that was the way that we were writing this. And so, but this still looks like we're starting from S naught, we alternate signs. So, and again, a prime is just the complement of A. Everything that's not You see? So this is an alternate way. This is the typical way of writing the inclusion-exclusion principle. If you want to know what's outside, of the union, then what you can do is from the total, which is usually known in the problems, you subtract our calculation right here. And so now it just happens to look like that. Make sense? So you have both versions. So I'm going to write both versions in general. So the first version, let me see. So this version corresponds to this version right here. Mm-hmm. But the typical version that you write the inclusion-exclusion principle is for the complement. So for this one, you just write S0 minus S1 plus S2 minus S3, and so on. And because we're multiplying the previous expression times -1, then the last term is actually -1 Sn. So this is the more typical way. They're equivalent, but this is a more typical way that the inclusion-exclusion principle is stated. Makes sense? So this is everything that's not in any of the sets. Mm-hmm. So I'm just going to say here that complement idea that we always use corresponds to that way of stating it. This one corresponds to our original idea for 2 sets and 3 sets, and I think it's more understandable as the first step. Is that okay? So that's the inclusion-exclusion principle. This is the inclusion-exclusion principle for 3 sets, and this is the inclusion-exclusion principle. They're equivalent versions, 2 versions of it for general number of sets. And then we can use it for different problems. That's all we're going to do today. We're just gonna use this idea and see how we can apply it for different things. Do you have any questions so far? Okay, so let's see a couple of examples, and then we'll remember that formula that we were using for the T numbers, the one with the dot product. That we never proved. I just told you, this is the way that you can compute it. So we're going to use the inclusion-exclusion principle to prove that formula. Right. So let's see. So E2 E3. What is this? Okay. So we're going to do the number of 5-letter words using alpha, beta, and gamma with at least one of the 3 letters missing. So Okay, so I'm gonna construct those sets. So I'm gonna say I'm gonna construct. I'm gonna call them A sub alpha, A sub beta, and A sub gamma instead of A1, A2, A3, or ABC. I'm gonna say A sub alpha is. Oh, maybe I should start with what's U. Okay, my universe is going to be the set of 5-letter words using alpha, beta, and gamma. No restrictions. Any 5-letter word. For example, I don't know, alpha, alpha, beta, alpha, gamma, or alpha, beta, gamma, gamma, alpha, or beta, 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 beta. any word, no restrictions. Okay, so these are some elements of you. Mhm. But the ones that I want to count are the ones that are missing at least one letter. So I don't want to count that one because it uses all the letters. I don't want to count that one, but I do want to count the beta, 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 beta. And maybe I should add another one. So maybe the alpha, beta, alpha, alpha, beta. Mhm. So I do want to count those two, but not the first two. Okay. So I'm going to say A alpha. So what's the condition is that they're missing one letter, at least one letter, right? So I'm going to make A alpha the ones that miss alpha. Make sense? So I don't want to count those. A beta is the set of words in U that means beta, that do not use beta. And A sub gamma is going to be the set of words that means gamma. So I don't want to count any of those. And now you can, if you want to have a visual in mind, here you have you have all your words, and then you have the ones that miss alpha, no beta, and no gamma. Yeah. So what I want is everything inside, right? I want the union. So we need to count how many. So we need the union. So this will be according to our formula. We just count how many in alpha, in A alpha, how many in A beta, how many in A gamma, right? And then we subtract the double intersections. And then we add the triple intersection. So I need to know what is the cardinality of all of those? So the cardinality of A alpha is A alpha is a set of words that do not use alpha. So A alpha is a set of words, set of 5-letter words using letters from no alpha, so beta and gamma. How many of those do we have? Well, 1, 2, 3, 4, 5 letters, and we have 2 possibilities for each, right? Because we can use beta or gamma. So that's 2 to the 5th. So A alpha is, cardinality of A alpha is 2 to the 5th. And similarly, A beta and A gamma are 2 to the 5th. So this is S2 minus S1 plus S2. You know, so it's another way to write it, right? Each row has S0, not S0, sorry, S1, 1, 2, and 3. One, two, and 3. And so from here, I just get that S1 is A alpha plus A beta plus cardinality of A gamma is just 3 times 2 to the 5th. Now let's look at, so that was kind of the first part. The second part, let's look at the cardinality of A alpha intersection A beta. So what is A alpha intersection A beta? Well, they're supposed to miss alpha and beta. So this is the set of 5-letter words using gamma. They cannot use alpha and they cannot use beta. So, this is just the set of the word gamma. This is just a set of the word gamma, 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 gamma. Just that one word. So this is 1. And the same for the other 2 sets. So A alpha intersection A gamma and A beta intersection A gamma is just 1. So this one tells me that S2 is equal to 3. Mm-hmm. And then finally, the triple intersection is empty, right? Because these will be words. I don't have any available letters. They cannot have alpha, they cannot use beta, and they cannot use gamma. So this is just 0, which means that S0, S3 is 1. So this implies that A alpha union A beta union A gamma, which is what we wanted, is equal to, I should say over here, what's the cardinality of the universe? So S naught is the cardinality of the universe, And these are 5-letter words using alpha, beta, and gamma. 1, 2, 3, 4, 5, and I have 3 possibilities for each. So that's 3 to the 5th. So this is as. Oh, I don't even need that because I'm actually looking at the actual union, not the complement. So this is 3 times 2 to the 5th minus 3 plus, sorry, that one is a 0. There's no word that satisfies that. Plus 0. So this is 3296 minus 393.
Do you mind walking through, like wrap out?
Yes. So let me just change this so that to highlight. Okay, so in general, you're gonna, when you have a problem like this, you're gonna have to identify what are you, like if you think that you can apply the inclusion exclusion principle, you want to identify your sets. So in this case, it says 5-letter words with at least one of the 3 letters missing, right? So because they need to miss one letter, I decided to make my sets so that each set is missing that specific letter, right? So this is how I created my sets. And so what we're looking for is all of this. Oops. So I'm looking for all of that. That's what I'm looking at. Okay? So because I want that type of union, then I know I can use the inclusion exclusion principle, and this is the way to use it. So here, this is just restating the inclusion exclusion principle. Mm-hmm. So the answer is just going to be this. So I need to compute these cardinalities. And because my sets are very symmetric, essentially computing one of those, just the cardinality of A alpha is going to give me the other two. Computing the cardinality of one intersection is going to give me the other two, and then the triple intersection. Mm-hmm. So each of these rows using our notation is the S1, the S2, and the S3. So in these 3 bullets, I'm just computing what's going to be each of these terms. The A alpha. So here you can see I have the A alpha, the A beta, and the A gamma. And here I have the double intersection, double intersection, double intersection. All of them happen to be the same. And this is a triple intersection. So to count those, I need to understand what those sets are. So the A alpha, that's just, first of all, so I do that and I figure out what those numbers are and, just add them up. So the S1 that I was looking for is just the sum of A alpha, beta, A beta, and A gamma. And so if I happen to see that they're 2 to the 5th, then I just add them and that's what I get, right? And for the double intersections, I get a 1, 1 plus 1 plus 1, that's 3. That's the second row. And then the triple intersection happens to be 0. And because the inclusion exclusion principle tells me to just add them up, alternate signs. So it will be 3 to the 2 to the 5th, 3 times 2 to the 5th minus 3 plus 0. And that's just putting those things here together, right? So the important thing here is these 3 bullets. I need to figure out what are those terms. And to figure out, I need to see in context what they mean. So A alpha is a set of words in U that means alpha. And from the set of 5-letter words that use alpha, beta, or gamma. So if they do not, if they miss alpha, so if they do not miss alpha, then they can only use beta and gamma. So that's why I restated what A alpha is. It's just a different way of restating A alpha. These two are the same thing, just different ways of stating what's A alpha. But if I understand that it's the same as this, then I can count how many elements I have. So 5-letter words, 2 possibilities for each spot. That's the 2 to the 5th. And I could have done the same for a beta or a gamma, because instead of having beta and gamma, I'm just going to have different symbols, but it's still 2 symbols. So each one of those is 2 to the 5th. That's what I get here, three of those, right? And then for the intersection, A alpha intersection A beta means that they have to satisfy the 2 conditions. So they need to do not use alpha, and miss beta. So do not use alpha or beta. And we're talking about 5-letter words that can use alpha, beta, and gamma, but cannot use alpha and beta. So they need to use gamma. So the only gamma. So that's the only word. So the cardinality is 1. There's only one word like that. And the same for the other double intersections. And when I put them together, that gives me 3. If you want, you can say 3 times 1. So that's the 3. And then for triple intersection, it would be words that use alpha, beta, and gamma, but at the same time, they do not use alpha, they do not use beta, and they do not use gamma. So there is no word like that. So that's 0. That's my S3. And now I just alternate, right? This minus that plus that. That's the inclusion-exclusion principle, and that gives me the 92. And so here's a follow-up. That's my example number 1. So here's a follow-up. Now count the number of 5-letter words using alpha, beta, and gamma. I'm going to count the complement right here that do not miss any letters. And that's actually E3, I think. So let me write it down. So find the number of 5-letter words using letters in the set alpha, beta, and gamma. With no letters missing. So they need to use all 3 letters. So here we use the complement idea. Use the complement. So I count all of the words with no restrictions, and that will be my U. I kind of went ahead and did it here. You see, I count all the words, all 5-letter words using alpha, beta, and gamma, no restrictions. That will be the U, the 3 to the 5th. And I subtract the ones that are missing something. And to subtract the ones that are missing something, I separate in 3 sets: the ones that miss alpha, the ones that miss beta, and the ones that miss gamma. I apply the inclusion-exclusion principle. But this is just, we already did that work. So we just use the version, when we use the complement, we just have to do, all the words. That's 3 to the 5th. So this is the cardinality of U, which is 5-letter words, what we did earlier. So I'm just going to write 3 to the 5th minus 93, right? So this one is just the cardinality of U, all the words, no restrictions. Minus the 93, which is the solution to the previous problem. Mhm. That would be my answer. But this is equivalent to the other version, the typical version of the inclusion exclusion problem. We want A alpha complement. So you don't want them to miss alpha. You don't want them to miss beta. And you don't want them to miss gamma. You see? Do not miss alpha. And do not miss beta. And do not miss gamma. That's really what we want, right? In terms of our notation. And so the inclusion exclusion principle says to do S naught minus S1 plus S2 minus S3. And now you just have to compute all of them. In our case, it was 3 to the fifth minus, there are three terms in S1, each one of 2 to the fifth, size 2 to the fifth. And then plus, there are three terms in S2, that's the double intersections of size 1 to the fifth, plus minus, there's one term of size 0. That's a triple intersection. Mm-hmm. Make sense? So that's kind of, what we did earlier, but I put it together. Imagine that you didn't have the previous theorem, the previous problem. How would you solve this problem? You see? So imagine that you don't have the previous problem. How do you solve this one? And the way that you solve it is you create your sets. The thing is that I don't know how to count this directly. With no letters missing, but I do know how to count. The total number of words with no restrictions. So that's why it's very easy to count with no restrictions. That's just a 3 to the fifth. And if I'm not allowed to use one of them, it's just going to be 2 to the fifth. If I'm not allowed to use two of them, it's just 1 to the fifth. And if I'm not allowed to use any of them, that's 0. Mm-hmm. And that actually corresponds to the S. 0 is 1, is 2, and is 3. Okay. Questions?
Professor?
Mhm.
So the last part, you says this is equivalent to the complement of A alpha to A gamma.
Yeah.
But how is it then? Why is it not a union? Because in the first problem, we define A alpha to be a set of words
Mhm.
that miss alpha, and
Yeah.
similarly for the others.
Mhm.
And we wanted to, we are looking at the all unions of all three to find the answer for the 5-letter words that use at least one of them.
Yeah.
So I think that's similar to the complement idea, but why is it's not in union, but it's in, I forgot what that notation is
So let me
called.
maybe draw another Venn diagram here equivalent to the one before, right? So we have A alpha, we have A beta. Actually, let's do this. So I have A alpha, A beta, and A gamma. Right? So U is all the words that use alpha, beta, and gamma of length 5. Mhm. Now, this circle is the ones that are missing alpha, but here I don't want letters missing, so I don't want to count A alpha, right? I don't want to count A alpha. I don't want to count A beta because those are missing beta, but I want no letters missing, so I don't want to count A beta. And I don't want to count A gamma because that one includes all the ones that do not use gamma, but I don't want letters missing. So what am I looking for? Well, this time around, I'm looking at this part. Oh. Okay. So this time around, we're looking at that. We're looking for that. We don't want to be in A alpha because those are the words that are missing alpha. This union are the words that are missing something. But this time around, I'm looking for the words that are not missing anything. So here we did the work for the union. Here we need the work for the complement. But we do have an alternative version of the inclusion exclusion theorem principle that actually counts the complement. So this notation right here, it's exactly this blue region here. Mm-hmm. The fact that they're not in A alpha means that they do not miss alpha. At the same time, they do not miss beta. That means that they're not in that circle. And at the same time, they do not miss gamma. They're not in that third circle. So they are completely outside. Mm-hmm. So we could have done this directly, but the definition of your A alpha, A beta, and A gamma is the same.
Okay, thank you.
We'll revisit this idea. Don't worry. Hopefully, by the third time that I mention it, it will make a little bit more sense. I just want to show you something. Does these numbers remind you of something that you've seen before? 3 to the 5th.
The binomial numbers on Pascal's triangle?
Yeah. So I have the 1, 3, 3, 1 that we don't see here, but the 3, 3, 1.
Yeah.
So that's one part of it, right? That's like I'm just going to write here 1 times 3 to the 5th. So I have the binomial numbers, right? But each one of those is like the first factor of each of my terms. The second factor, I'm alternating signs, right? I'm alternating signs, and I have the powers of 3, 2, 1, and I'm gonna write a 0 here just because it kind of follows the pattern. It doesn't matter, right? It's the same thing. And I'm alternating signs. So that's positive, negative, positive, negative. So this expression right here, maybe I'll add this one also with red because I didn't have that there, but it doesn't hurt if I add the one there. Mm-hmm. Is this dot product? Remember, just entry times entry. So it's just first entry times first entry, second entry times second entry, and so on. Mm-hmm. And then add them up. So this is just a different notation for that. And remember what this is?
It's a T number.
It's a T number, right? So this is the T number 5, 3.
Is your second 3 1 in that first grouping?
Oh, oh yeah, I didn't. Sorry, I didn't.
I just struggling enough.
Yeah, sorry about that. So yeah, 1, 3, 3, 1. Yeah. So that's T5, 3. Mm-hmm. So then let's use the inclusion exclusion principle to write TMN, the T number TMN, like this, right? We just did it for five letters, three available. So those are your boxes. The alpha, beta, and gamma are your boxes, and the positions of the letters are the balls. Mhm. So how can we set it up? Let's see. So we're going to use the inclusion-exclusion principle. To compute the to compute TMN. That formula that we have. So how can we deduce it, right? Because I just gave it to you, but how can we actually deduce it? Mm-hmm. So I have, TMN is the number of ways to distribute m different balls into n different boxes. That we can count very easily, but what makes it difficult is that there are no empty boxes allowed. Remember, if we don't have this restriction, it's just each element has n boxes to go into, and so your answer is n to the n. So without this second line, it would be very easy. Use the n to the n. But because we have this, then we're in a little bit of trouble. And so what we do is we're going to, because we don't want empty boxes, we're going to define our sets in terms of what we don't want to happen. Mm-hmm. So I'm going to define AI to be the number of distributions. Well, actually, first I'm going to define my universe. The universe is just going to be those distributions with no restrictions. Okay? So U is going to be the set of distributions of those m different balls. Ball 1, ball 2, ball 3, and so on. So these are like specific m balls into n different boxes. And those are specific boxes, box 1, box 2, box 3, and so on. Mm-hmm. And so I'm going to define my sets. AI is going to be the set of distributions. So here I'm going to add a restriction. The set of distributions in U, of those m balls into those m boxes that do not use, that leave box I empty. I don't want that to happen, right? I don't want to have empty boxes. I don't want to have empty boxes. So my AIs are defined by what I don't want, the minimum that I don't want. So I have to use box I. So I'm going to define AI as the ones that do not use box I. Those are my sets. So this I'm going to define for I between 1 and n. So I have n sets. So I have A1, A2, all the way to AN. I have n sets. And then what do we want? We want all the distributions that are not in my AIs. The AIs are subsets of U, right? So I have U that has all my distributions, no restrictions, but I want the ones that do not have empty boxes, right? So I don't want the ones in the AIs. So what I want, what we need, is the cardinality of the complement, the intersection of the complements. So I don't want the ones in AI. I don't want the ones in A1. I don't want the ones in A2. I don't want any of those. That's what I want. Yeah. Because those are the ones that, we don't want empty boxes. The ones in A1 fail because they don't use box 1. The one in A2 fail because they don't use box 2, and so on. So all of those fail. So that's why I want the complements, because the intersection of the complements, those are the ones that do not fail. So, and according to the inclusion-exclusion principle, that will be S0 minus S1 plus S2, and so on. Right? And now I just need to compute what is the intersection, what is the S0, S1, S2, and so on. So what happens is that if you want to know what is SK, so to compute in general SK, SK is made of terms of this, of this form. If I have K of these elements intersecting, so that means this is the set of words, set of distributions in U, not using box I1, box I2, box IK, not using those K boxes. You see? How many of, and no other restrictions. So I'm allowed to use all the other boxes with no restrictions, maybe some of them, not necessarily all of them. And so the cardinality of this is, now I have n minus k boxes. So n minus k boxes. I'm not using those k, but I can use all the others with no restrictions, and I have n balls. Mm-hmm. So these are the number of distributions of n balls into n minus k boxes. No restrictions, right? So it's like the first column in my distributions table, first column, first row. Uh-huh. And so that implies that the SK is, I choose the K boxes, the K sub-indices here, so that's the number of terms for my SK, that's n choose K, and then I multiply times the cardinality of each one of them, which means that what I want is simply the sum from k equals 0 to n of negative 1 to the k, sk. This is just that, okay? And this is the inclusion exclusion principle. This is just by the inclusion exclusion principle. This is what I need, okay? And so just replace the sk, and so now I just have the negative 1 to the k, n choose k, n minus k times n, from k equals 0 to n. And this is exactly the formula that I gave you. So this is exactly the dot product. N choose 0, n choose 1, n choose n,
dot product with negative 1 to the 0. Yeah. And so let me just write it like this. N to the m minus n minus 1 to the m n minus 2 to the m minus n minus 3 to the m. And just, keep alternating until you get to negative 1 to the n and minus n to the m. That's the 0 that we always get at the end. That's the formula that we have, right? But the very first time that I gave you this formula, I actually gave it to you like this. Like this. The dot product was the easier way to remember it, but that was the formula that I really wanted to prove. Okay, so that's all I wanted to do today. I know I'm over by 2 minutes, so but yeah, so this is the inclusion-exclusion principle. I'll retake this at the beginning of the first class after the spring break, but what I really want to do is kind of leave this behind a little bit. So I'm going to assign some problems, but I think some wiki problems, but I'll send you a list, and it's going to be, we're going to make them extra credit for people to recover from the exam if you didn't do too well or something like that. So, but I wanted to go over this before the spring break, so in case you wanted to understand it during the spring break, when we come back, we'll just do graph theory. Okay? And we'll go over the exam, and yeah. Okay, guys, I'll see you. Enjoy the spring